Okay, sir.
Yeah. So sorry for the interruption. So so now we are planning to implement power and communication system with the help of Wavelet transformation. For that, as I was telling, we need to design filter banks basically. So minimum of two filter banks are very much essential. The first one is the synthesis filter bank, another one is the analysis filter bank. Because once we speak of a Wavelet transformation method, so Wavelet transformation method basically having a square shape function, which is continuous in nature and which is, sorry. So Wavelet transformation basically it will be having a square shape function which is continuous in nature and periodic in nature. Therefore now within this we are going to transmit the information. Within this we are going to transfer the data that is to be transmitted from one point to another point. So now, so first what exactly we wanted to do here is we need to identify all the system. We need to identify all the symbols which are crossing within the threshold value. Okay, depending upon that, we need to transmit the information either through the high pass filter or the low pass filter. Then we need to have the comparison. That is why we need to design two filters. The first, the synthesis filter is to make the normalization of the symbols, and second one is to have the analysis. So this analysis filter is mainly used to have the comparison. It's mainly used to have the comparison. So by the combination of these two, we could able to have the implementation of power line communication with respect to Wavelet transformation. So now one more important thing that we can observe over here is, so here we are making use of Z transformation, where f of k, where f of k represents the actual symbol that is to be transmitted, f of k represents the actual symbol that is to be transmitted, and for that we are taking the Z transformation. The very purpose of having the Z transformation is because we can have the convergence value. We can have the convergence value. So this is a very important aspect of designing of Wavelet transformation with respect to the transformation. And we know that whenever we wanted to find out the critical values and the comparison purpose, we always go for the Z transformation. So this is the equation for the synthesis filter and this is the equation for the analysis filter. And at this point of equation, we are having the relationship between synthesis filter and the analysis filter. Therefore, if we can have the equation between the two types of filters. So now this is the mathematical modeling of the filter circuit for the Wavelet transformation. So now this is the second approach. The first approach is the filter design. This is the second approach, which is called as the multi-resolution analysis. So now it's basically a comparative approach and also the iterative approach. So I'll take a signal that's been transmitted. So now depending upon the amplitude of the signal and the gain of the signal, if the gain of the signal is high, then we are going to pass the signal into the low pass filter. Therefore, we could able to minimize its gain. So again, we need to go for the downsampling. And again, after the downsampling, if the amplitude is more than that of the ma'am, to hear ma'am. So again, we need to go for the downsampling. Again, we need to do the comparison. After downsampling, if the amplitude of the signal is high or the gain of the signal high, means again we need to go for the low pass filter. Therefore, we could be able to minimize its gain. For example, at any moment of time, if the signal is having if the gain within the threshold value, means we need to pass it through the low pass filter. Depending upon the gain value, we need to pass it through either through the low pass filter or the high pass filter. Therefore, after n number of iterations, therefore we'll be having the normalized value. Therefore, whenever if we normalize the signal, there's a very less chances of distortion of the signal. Therefore, as I told, multi-resolution analysis is the one which is basically an iterative method. So next is regarding Haar wavelet. That means designing of a Wavelet transformation with respect to filter circuits. So in which the most common type of wavelet circuit is the Haar wavelet. So Haar wavelet is the first type of wavelet and it is a very fundamental type of wavelet. now hard wavelet is the one which is we having two describing function. The first one is wavelet function and another one is the scaling function. So as I discussed earlier in the case of introduction, so we need to pass a signal. We are going to pass the signal within the R wavelet describing function. Whereas describing function for the R wavelet is been given by this, that is psi. So it is given by the equation psi. That means it is having a continuous periodic square signal. Fine. So the whatever the signal that's to be transmitted is being made to pass through this higher wavelet, and all the signals it's going beyond it, it's been passed through the low pass, and remaining signals have been passed through the high pass. Therefore, we can have the normalized value. Then once the signal has been normalized, we need to pass through a scaling function. We need to pass through a scaling function. Just ensures that so the signal is within the range. Okay, therefore, and whenever we ensure the scaling function, there is a very less possibility of distortion of the signal. Therefore, addition of the noise signal becomes very least, or it is ignoring. Therefore, that's what. So, how exactly we frame the mathematical equation and how we frame the scaling function and the describing function, which decides the accuracy of the wavelet transmission. So the first type of wavelet transformation that we use is the hard wavelet transformation. The second type of approach is the debounces. So whereas in the case of hard wavelet, the describing function for the hard wavelet and scaling function is fixed. It's always these are the describing functions. Whereas in case of debounces, so debounces is the second type of approach in which the describing function for the scaling function and the describing function for the wavelet transformation is depending upon the type of the signal. Okay. For example, I may transmit some power signal. I may transmit some power signal. Therefore, it will be having a sinusoidal waveform, something like this. Okay. So in the next case, I may pass some sort of audio signal. Audio signal will be depending upon its amplitude. And in the next case, I may transmit some sort of video signal. Okay, therefore, I'm going to transmit different types of signals. Therefore, in the case of debounces wavelet transformation, the describing functions of the scaling and the wavelet will be adjusted as per to the different types of the signal. Whether it is an audio signal, video signal, or the power signal, the describing functions are going to adjust depending upon the type of the signal. That's what here we can see. Depending upon the type of signal, we can see that the waveform will vary depending upon the type of the signal. Okay, that we are going to design the describing function like that, mathematical equation like that. And the third, and this is the analysis. That means here we can see the first two waveforms represents the analysis of the low pass filter. So this is for the analysis filter and this is for the synthesis filter. And the next two waveform will represent the analysis of high pass filter, and again for the analysis filter and the synthesis filter. So now we can see we'll be having some threshold value. We can have some threshold value. Therefore, some of the symbols are becoming beyond the range. So some of the symbols are becoming beyond the range. Therefore, and such type of signals are to be made to pass through the low pass filter. That is why we are adding it under the low pass filter. Okay, therefore, whenever we make it to pass through the low pass filter, so these symbols are becoming the normalized value. These symbols are becoming to the normalized value. ಅದರಲ್ಲೇ ಲಾಗಿನ್ ಆಗಿ ಸೇಮ್ ಅದೇ ಹೌದು. So next, whenever they go through the synthesis filter, so and again, so we need to pass through the low pass filter. Therefore, we can have the normalized value. So this is the analysis of low pass filter. And now, when we go for the high pass filter, see here we can see some of the symbols for which the value will be lesser than the normalized value. So those type of signals are made to pass through the high pass filter. Therefore, we can increase its gain. Okay, therefore, once we have the normalized value, therefore all the symbols are become within the normalized value. Okay, that is the analysis of debounces wavelet transformation. That is the second approach. So next is regarding bi-orthogonal wavelet filters. So now again, so in most of the analysis with respect to Texas Instruments, they are making use of bi-orthogonal wavelet filters, because here the same filter is divided into another two types. The same filter is divided into another two types. The first one is reconstruction or the decomposition, and another one is the reassembled. Okay, so therefore we are going to have the same filter design which is divided into another two types. Therefore, since we are designing the same filter with another two next level, therefore we can ensure the efficiency to the greater extent. Therefore, now we can see, you know, this is these two are the waveforms for the low pass filters, and this is the analysis for the decomposition, and this is the analysis for the reconstruction, and this is the analysis for the high pass filter. This is the analysis for the high pass filter, this is for the decomposition, and this is for the reconstruction. So now, so once we make the signal to transmit through these filters, therefore we can say that the signals are been getting normalized. Okay, therefore, once the signal has been getting normalized, there is a very less chance for the addition of the noises. So therefore, obviously, we can ensure the higher efficiency of the transmission. So next is regarding reverse by orthogonal. This is the fourth method. This is the fourth method. Therefore, as we can see, the concept is just similar to the previous one, whereas bi-orthogonal filters are being used in the transmitter side, whereas a reverse bi-orthogonal wavelets are being used in the receiver side. Therefore, from these few waveforms, we can observe that. So after the filtering of the signals, therefore we can say that most of the signals are becoming within the normalized value. Okay, so most of the signals are becoming within the normalized value. Okay, so these few signals again they have to make to pass through the high pass filters with a higher gain. Okay, therefore we can go for the normalized value. So this is regarding the performance analysis. As a summary, I can say that the implementation of power layer communications can be done with respect to wavelet transformation, in which the first approach is the Haar wavelet, in which we'll be having the two describing functions. Next one is debouches, in which the describing functions are with respect to the type of the signals. Next one is bi-orthogonal, and next one is the reverse bi-orthogonal. So these are the four different approaches for the designing of power link communication with respect to wavelet transformations. So now, the very purpose of wavelet transformation is the one in which wavelet transformations are the replacement of FFT and IFT algorithms. FFT or IFFT algorithms. IFFT algorithms. And we know that FFT and IFFT algorithms are the replacement of differentiation and the integration. Differentiation and the integration. That means the concept of calculus. Calculus, that means delta t tending to 0. The analysis of any particular parameter with respect to 0. And so calculus is the one which creates a link between nature and the mathematics, which creates the relationship between nature and the mathematics. Okay, therefore this is the link, and this is the very purpose of using the wavelet transformation. So calculus is the one which creates a link between the nature and the mathematics. How exactly we can represent nature in terms of mathematical equation, whereas the calculations is been analyzed with respect to derivatives and the integration. And this calculus is been replaced by FFT and IFT algorithms, because these are the one which gives us to the solution for infinite equations also. Now these days, FFT and IFT algorithms are being replaced by wavelet transformations. That's why wavelet transformations are being considered as the booming technology in these days in order to get the solution for the infinite sequences also. So now these are regarding the performance analysis. The different parameters which are taken to for the analysis is, the first one is the bit error rates, which represents a ratio between the total number of bits that are being added with the noise signals, which are called as the error bits, and total number of bits that is been transmitted. That means whenever we transmit some of the information from one point to another point, it is been transmitted to receiver. Therefore, total number of bits that is been transmitted is the denominator part, and total number of error bits. That means during the transmission, some of the signals may get distorted. Okay, they are representing the error bits. The ratio of the two representing the bit error rates. Next is regarding packet error rate. That means we are transmitting the symbols in the n number of packets. So now within that, how many packets are being getting distorted, and the total number of packets. So next is regarding peak to average power ratios. That means whenever we transmit the symbol, so whenever they transmit the symbol, they have to transmit with the suitable dielectric medium. Okay, therefore, these symbols will be having both electric field properties and the magnetic field properties. Electric field property is the one which analyzes the voltage that's transmitting through the signal, and magnetic fields are the one which analyzes the current that's flowing through the symbol. Okay, therefore all the symbols will be having some sort of the power dissipation. Okay, so once you plot the power curve, so it will be having the peak value and the average value. Okay, therefore let me take the ratio of peak value to the average value. Therefore, that is one of the important parameters. It is called as peak to average power ratios. Okay, lower the value of the peak to average power ratios, better will be the efficiency. So now these are some of the analysis part. That means we are implementing the wavelet with respect to different approaches. The first one is a reverse by orthogonal, as I told, the fourth approach, and by orthogonal, there is a third approach, and these are some of the analysis with respect to Haar wavelet. And we are having Haar wavelet also. So I told four different approaches. Therefore, I'm taking the net list of all the four different approaches. So now this is regarding existing. That means whatever the method that I told. That means in the existing technique. That means in one of these slides that I told the existing technologies. Correct? So I think it is in slide number 4. I told about the. Now I'm referring to slide number 11. I'm referring to slide number 11 here. I have showcased regarding 4 different techniques. So I'm considering the performance analysis of all these 4 techniques. Therefore, in which the first technique has been implemented with respect to Haar, and second and third and the fourth one, and so on. Therefore, from this, for example, if you consider the Haar wavelet, so with respect to the existing technology, bit error rate is around 19 exponential minus 3. 19 into 24 minus 3, that is the range of the bit error rate. Now, with respect to the implementation of power and communication, with respect to Haar, we could able to get the bit error rates in the range of 9.5 10 to the power minus 5. Almost we can say that almost that is 95.6 10 to the power minus 4. That means we could able to reduce by 1 by 10. We could able to get the result by 1 by 10. Therefore, again, since it is in the negative exponential, it's a considerable difference. Okay, therefore, it's better to implement multiple input, multiple output OFDM with respect to data transformation. And once we go for reverse by orthogonal or the gain, therefore we could able in all the respective values, therefore we could able to get the difference. That is better results with respect to wavelet. And you can see these are some of the performance parameters that we have considered for the analysis. Therefore, multi-carrier modulation system is being used. Number of sub-channels are 16, and total number of data per channel is around 12. And operating frequency is 4.3 megahertz, because this frequency will come under the radio frequency range. So now this is the performance analysis. So now here we are doing the analysis of noise parameter with respect to bit error rates. So I'm considering both the type of noise signals, the Gaussian noise, which is one of the most common noises, and the Racian noise. Racian noise is the critical noise. Therefore, from this we can observe that whenever the noise parameter is been increasing, the corresponding noise, the corresponding bit error rate is been increasing. And you can see here, it will be in the range of 10 to the power minus 4. That means in the bit error rate is been increasing in a negative exponential. So therefore, it's a very good sign. It's a very good sign. Second waveform represents comparison of signal to noise ratios versus bit error rate. Therefore, it's a conventional OFDM. That means whenever the OFDM system is been implemented as it is, as I showed in the slide number 3, conventional OFDM system. Whenever the OFDM system is been implemented with respect to wavelet, it's been represented by loop. Okay, therefore, from this we can observe that when we have a comparison between SNR and the bit error rates, we can able to observe a reduction in the value when we implement it to the wavelet. That is what the observation that we can do. And this is the performance analysis in all the performances. So this is for the additive white Gaussian noises and the different approaches. So for the different gain value. Okay, here we are implementing for the different gain values. So just we keep on vary the gain of the different filter circuits. Therefore, we can see the performance has been reducing. And here, this is the different approaches. In all the approaches, this is the waveform representation for the different approaches of wavelet implementation. The first one is the undistorted wave. Okay, this waveform is representing the undistorted wave. And second one is the peak cancellation. As just now I told, that means we need to identify the peak and we need to cancel this. That can be done with the help of suitable scaling function. That is what I told. Whenever we design a suitable waveform, that is wavelet waveform with the suitable describer function. Therefore, we can able to get the desired of this thing. Clipping. So clipping is the third approach. Therefore, in all the different approaches, therefore we can say that reduction in the packet error rates. Therefore, we are decreasing in the negative scale. The last one is additive white Gaussian noise. That's one of the critical types of the noise signals. So this is regarding one of the interesting topic, that is the analysis of intercarrier interference. That means we'll be having the signal that's been transmitted, and those signals are given by the n number of carrier signals. Carrier signals. That means we may be having hundreds of thousands of carrier signals, whereas these two carrier signals will be orthogonal to each other. Okay, so the concept of intercarrier interference is the one in which carrier signals itself, they may be getting distorted. The carrier signals are basically the envelopes for the to carry the signal. Therefore, sometimes the carrier signal itself may get distorted. Okay, so once they get distorted, obviously the signal is going to get disturbed. Okay, therefore, so at this moment of time, we are analyzing the concept of intercarrier interference, whereas this waveform basically represents different types of input signals. As we can see, we will be having the rectangular signal and raised cosine function. Raised cosine function is one of the interesting, that is raised cosine is given by sin x, sin x by x, sin x by ax, and we need to go for the integral with respect to dx. It's a very interesting type of mathematical equation, that is one type of input signal that we gave, and better than raised cosine. And next is regarding coordinate sine function. That means we'll be having power pulse. Okay, because power line communication is the one. Power line communication is the one in which we will be having analog signals plus digital signals along with the power signals. Analog and digital signals are the one which will be having lower amplitude, okay, and higher frequency, higher frequency. And power signals are the one which will be having lower frequency and the higher amplitude, higher amplitude. Therefore, it's very much difficult to combine all these types of signals because frequency range will be different, amplitude will be different. Therefore, it's a very challenging task. Okay, that's why the Wavelet transformation will also support for the power pulse. So now here, so in the second waveform, we are doing the analysis of frequency versus carrier interference rate. Therefore, from this we can observe that for different types of symbols, as and when the frequency is been increasing, therefore corresponding carrier interference rate is been reducing. Carrier interference means the interference, that means we'll be having first carrier signal and second carrier signal. Therefore, interference between these two waves is been reducing. Okay, once we have the proper carrier signal, ultimately we can ensure the corresponding efficiency of the transmission. The next is regarding intercarrier interference. So and again for the different types of signals, so as and when we increase the frequency, the corresponding CIC, the carrier interference rate is been reducing. At some particular point, it's becoming equal to 0. So this is regarding turbo hard discrete Fourier transformations. That means we are going to add one more block in which we'll be having a signal. Those signals are been divided, then they are made to pass through the low pass filter and the high pass filter. So once we get the normalized value, therefore they are going to add all the signals. We are going to add all the signals. That is the concept of turbo encoder. Now, if you observe this block diagram, if you just ignore these parts of the block, is just like the conventional type of the modulator and demodulator part. So this is the implementation of turbo decoder. As I told, it will be having basically an encoder circuit which split up the signal. So this is the performance analysis. Therefore now, so whenever MIMO system is being designed with the turbo wavelet transformation, so now we are doing the analysis of signal to noise ratio and bit error rates. Therefore, these are some of the waveforms which are representing the proposed technique. Proposed technique in the sense implementation of wavelet transformation with respect to turbo encoder. Okay, so these are the wavelet transformation without a turbo encoder. Therefore, from this we can able to observe that the ratio between signal to noise ratio and bit error ratio is been reduced drastically by a power of 10 to the power of -2. Fine. So here we are implementing for different types of symbol rate, that is 256, 512, and 1024. So once we ensure for these ranges, so as and when the total number of constellations is been increasing, obviously we can ensure this thing. and this is for QPSK. Similarly, we can repeat for BPSK, the binary phase shift queuing, and the quadrature amplitude modulation. In all the approaches, we can see reduction in the bit error rates. That is what exactly we wanted. So once the bit error rate is been reduced, obviously the efficiency becomes the higher value. So this is for the analysis of additive white Gaussian noise. So next we are taking for the Raysian channel. The Raysian channels are highly sensitive. Whenever they having the combination of the signal, therefore we go for the Raysian noise. So here also these waveforms are representing the proposed technique, and these are representing the wavelet transformation without the turbo encoders. Therefore we can see a drastic decrease, okay, in the bit error rate. So once the bit error rate is plus, efficiency of the transmission will be high. Capacity of the transmission and quality of the transmission is also high. So this is regarding the performance analysis. So next is regarding PAPR. The next one is regarding analysis of PAPR reduction. So PAPR stands for the peak to average power. So once the waveform is been transmitting, it will be having the peak power and the average power. So we are going to take the PAPR. So PAPR basically represents peak to average power ratio, signal to noise ratios, and bit error rates, inter-symbol interference, and inter-carrier interference. Okay. So when PAPR is less, we can say that all these parameters will be less. That's why the PAPR plays a very important role. Whereas the major cause for PAPR is the making use of non-linear components, because most of the filter circuit that we use is a non-linear component. Therefore, it's ultimate to make use of non-linear component. Therefore, PAPR will be high. But whenever we implement OFDM system with respect to wavelet transformation, because of the describing function, that is scaling function, we could able to minimize the amplitude. Therefore, there is a very less scope for higher value of the PAPR. Therefore, since the signal itself are being normalized, as I told before, therefore there is a very less chances for getting the higher value of the PAPR. Now, these are some of the approaches. So now, the PAPR analysis can be done by three different methods. So the first one is selective mapping. That means we'll be having a signal that's to be transmitted, then that's be converted into serial to parallel. That means the signal is being converted into number of segments. Therefore, here we are having the normalized, that means threshold value. Those threshold value will be convoluted with the actual signals. Okay, therefore, once we convolute the signal with the threshold value, we are going to get the samples. So if these samples are within the threshold value, then we can say that the PAPR is within the range. Then we are going to have the transmission. For example, if the symbol S is having higher value of the threshold value, means we need to go for the normalization through the suitable high pass and the low pass filters. This is regarding partial transmission sequencing. That means we are going to have the symbols. If the symbol power dissipation is high, means we need to take it to the peak power optimization, in which the power dissipation will be optimized. Then we are going to feed back into the actual system. If the power dissipation of the signal is within the range, means we are going to transmit the signal as it is. So basically, it's a comparative approach. We are going to compare the power dissipation, and depending upon the value, we are going to have the optimization. So now, this is what the mathematical modeling. Therefore, we need to go for mathematical modeling of SLM, that is selective mapping, along with partial transmission sequencing, and along with the clipping. Therefore, we are going to combine all these techniques. Whereas partial transmission sequence is a different technique, clipping is a different technique, and selective mapping is a different technique, in which we are going to combine all these three. Therefore, we could be able to minimize the power dissipation. And clipping is one of the techniques that is used in the wavelet transformation approach. Therefore, this is the describing function for the clipping techniques. So this is the representation in terms of decibels, and this is the equation for the clipping. It's a very simple technique. So therefore, once we come to the analysis part, so we are going to consider the different subcarrier signals. Total number of blocks used is 4, and we are implementing for the QPSK and additive white Gaussian noises. Therefore, we can see, so the proposed, that means OFDM is a fundamental logic, selective mapping, partial transmission, and combination of selective mapping and the partial transmission, and proposed. The proposed means combination of clipping, selective mapping, and the partial transmission sequencing. Okay, from all these techniques, we can say that when we compare the comparison between PAPR versus complementary cumulative distribution factor, therefore we could say that it's having a very least value. So this is for the 1024 number of constellations, and next we're having for 1024 number of constellations, 512 number of constellations, and 256 number of constellations. Therefore, in all the cases, we could able to get the reduction in the PAPR. So this is again for 128 number of constellations, and here we can see the comparison between racemium channel and the additive white Gaussian noises. Okay, therefore, we can say that racemium noise is highly sensitive. In that type of channels also we could be able to get the reduction in the PAPR. So that has been happened because of the combination of SLM, PTS, and the clipping. So now this is the analysis of different signals, 1024 and all those things. So with respect to signal to noise ratio and the bit error rates. What I wanted to say here is implementation of selective mapping, partial transmission with the clipping will reduce the PAPR. So once the PAPR is plus, bit error rates, signal to noise ratios, and intercarrier interference, all those values will be minimized, which improves the efficiency. So now this is the experimental setup. Therefore, for the implementation of OFDM technique with respect to Wavelet, therefore we have to make use of these are the system configuration. So if you want me to share the PPTs, this is what the system configuration is. This is regarding the conclusion. So my main aim is to implement OFDM techniques with respect to wavelet transformation. So in which wavelet transformations can be implemented with different techniques. The first one is the HAR. Next one is debouches. Next one is by orthogonal and orthogonal. So now these are the different techniques, and my main intention is to analyze bit error rates and signal to noise ratios and PAPR. So now these are the different PAPR. Okay, these are the different approaches. So once we implement OFDM with respect to wavelet transformation, therefore all these parameters can be reduced effectively. So this is regarding applications. So in almost in most of the communication systems, we can see the application of wavelet transformations. So this is the end of my presentation. If you have any queries, I'll answer. So so last but not the least, I'd like to acknowledge my guide and my well-wisher and everything for me, that is Dr. Nataraj sir, Dean and Director R&D DBIT, and Dr. Rekha KR Madam, my research supervisor, who supported me at different intervals of my research work, and Vidyavardhaka College of Engineering, wherein I'm currently working, and DBIT for giving me an opportunity to present my topic, and Institute of Engineers for the association, and BSNL and Texas Instruments for providing the technical support. So with this, I conclude my presentation. If you have any queries, I'm ready to answer. Please. Any queries, ma'am? Hello.
Hello, sir.
Yes, ma'am. Huh. Hello.
Participants, if you have any queries, you
Yes.
can
Yes.
ask.
If any queries, means I'm ready to answer. Or else you can text me. You can put the questions in the text box, chat box. I'll answer to it. Impulse noise modeling techniques. Okay, impulse noise techniques modeling. So impulse noise technique modeling is the Raysian noise channels. The first one is the Raysian noise analysis. Raysian noise analysis is there, in which basically we consider the signal that is to be transmitted, and that is being given for a FFT algorithms. Okay, for impulsive noises, the implementation of with respect to wavelet transformation becomes quite difficult. That's why we go one step backward. Therefore, it's better to make use of FFT and IFT algorithms, because impulsive noises is basically an infinite numbers. It will be having an infinite numbers. That is why it's better to make use of FFT and IFT algorithms. That is one solution that I can suggest. It's quite difficult to go for mathematical modeling with respect to wavelet transformations. Mathematical modeling becomes quite huge. It is possible, but it is feasible to make use of FFT and IFT algorithms. Thank you, sir. Thank you, Gopal Krishna, sir. Thank you, sir. Okay, it's my privilege. Any more questions, sir?
If there any queries,
If you any queries, please put it to my mail.
raise your
My
hand.
my mail is been
Sir, if
displayed
any,
here. I can clarify to your questions, and I can also share some of the work that I have done, simulation part, and also I can give whatever the suggestions that's from my side. Okay, with this I conclude. I thank the team of DBIT, especially Dr. Natraj sir. It's my immense privilege to be a part of this event, and Dr. Rekha madam, who is my supervisor, research supervisor, and Vidyavardhaka College of Engineering, wherein I'm working, and all the participants for your patience listening. And I would like to ask excuse because my explanation is quite faster. I need to overcome it, but I ask excuse from you people. If you have any queries, you can put a mail or you can WhatsApp me. Up to my level best, I'll give the suitable suggestions from my side, or I'll get the contact from industry, that's from Texas Instruments or BSNL, so that I can give the suitable suggestions. Thank you, sir, and Anand sir, Vishwa sir, Divya Patel madam, Jay Shri.
okay, thank you, sir. Thank
Thank
you
you,
for the
ma'am.
wonderful session,
Thank you, ma'am.
Dr. Lokesh, sir.
Thank you,
It
ma'am.
was very informative session. Okay, I conclude this session.
Yes.
I want to thank our management for supporting to arrange such events. I also thank our Dean and Director, Dr. Natraj KR, Department of R&D, Don Bosco, and I also thank our principal, Dr. A. Madri Naidu, and I also thanks all the participants for